Okay, so welcome everyone, and a warm welcome to Nama Hallakoun from Weizmann, uh, who did not cancel the semester, and we hope to thank her by inviting her again next year for the full hospitality. She will tell us about companions and debris around white dwarfs. Feel free to ask questions at any time, and let's have a start.
Okay, so thank you for inviting me to give this Zoom talk. And as I said, I'm a new postdoc at the Weizmann Institute. And the work I'm going to show you today is based on works I've done together with Dan Maoz from Tel Aviv University, who was my PhD supervisor, and also with many other people whose name will be mentioned in the relevant slides. So let me start by giving you some quick motivation for my talk, and that my title is quite broad, and let's see what exactly I'm going to talk about. So if you look at the background image of the night sky, you can see Orion here, and here is Sirius. By the way, do you see my cursor? Okay, so here we have Sirius, which is the brightest star in the sky. And as you probably know, Sirius is not just a single star. It's in fact a binary consisting of an A-type star, the bright star of the two, and a white dwarf companion. So white dwarfs are interesting. They're interesting because more than 97% of all the stars in our galaxy will eventually end their lives as white dwarf. But in this talk, I'm not going to talk about Sirius-like systems because what happens when we take a Sirius-like system and move it farther away from us is that we only see the brighter companion. It dominates the spectrum and we can't see the white dwarf. So what am I going to talk about? I'm going to talk about white dwarf that on a single look like a single star. On the first look, might look like single star, but when you look closely at them, you might see the evidence for a stellar companion or maybe a white dwarf companion, and then we have a double white dwarf, like here. And in fact, the Sirius system in many years from now will eventually turn into a double white dwarf when the A-type star companion will evolve into a white dwarf. Or maybe we can see evidence for a planet or planetary debris, for example, a debris disk. So these are the type of systems I'm going to talk about today. Now, let me give you some quick facts you need to know about white dwarf. And basically everything that I'm going to say to you today is based on these few facts. So first of all, white dwarfs are very dense. You take a mass of the sun and you squeeze it into the size of the Earth, and then you get densities of 10 to the 4 to 10 to the 7 gram per cubic centimeters. And because they are very dense, what we get is gravitational settling. If you look to the right, you have a cartoon version of a typical white dwarf. We have a carbon-oxygen core surrounded by a helium envelope, and on top of it, a hydrogen atmosphere. So basically, because of the high surface gravity, what we have is that all the heavy elements relatively quickly sink below the atmosphere of the white dwarf. So the heaviest elements present will be in the core of the white dwarf, and when we move outwards to the surface of the white dwarf, we'll get lighter and lighter elements. So when we look at the white dwarf, we expect to see, we see only the atmosphere composition, and we expect to see only the lightest element that is present. Now, about 80% of the white dwarf looks something similar to that. They have a hydrogen-dominated atmosphere, and we call this white dwarf dA. This is just a notation that is based on the optical spectrum of the white dwarf. It means if we have a dA white dwarf, it means that if we take a spectrum of it in the optical range, we expect to see only hydrogen lines, hydrogen absorption lines. Now, about 16% of the white dwarf have helium-dominated atmosphere, and we call them DB. And basically, it means that they actually have no or almost no hydrogen. So when we take a spectrum of DB white dwarf, we see only helium absorption lines. And there are some other types of peculiar white dwarf, but we don't get into that right now. So as I said, most of the white dwarf have a hydrogen-dominated atmosphere, and when we take a spectrum of these, we see only very broad Balmer line. So this is an example for a typical white dwarf spectrum from the SDSS survey. You can see here this black body continuum, and on top of it, you have this hydrogen Balmer absorption line, and they are very broad because of pressure broadening because of the high surface gravity of the white dwarf. Now, keep this in mind for later when we talk about measuring radial velocities of white dwarf, because the width of the absorption lines makes it very difficult to measure accurate radial velocities. And we'll get back to that in a few slides. Another fact you need to know about white dwarf is that they cool as they age. White dwarfs don't produce energy anymore. When they were main sequence stars, they were fusing hydrogen into helium, but that already stopped, and they just start their life very hot and slowly cool down over billions of years. And it means that a white dwarf can serve as cosmic clocks, because if we know the white dwarf chemical composition of the atmosphere, whether it's a DA with hydrogen-dominated atmosphere or a DB with helium-dominated atmosphere, and so if we know the chemical atmospherical composition, and if we know the mass of the white dwarf, we have a one-to-one correspondence between the effective temperature of the white dwarf and its age. As you can see here, these are cooling tracks of DA, hydrogen-dominated white dwarf. And each line here of different color correspond to a different mass of the white dwarf. So you see that if we know that this is a DA white dwarf, and we know that it's, for example, a 0.6 solar mass white dwarf, which is a typical mass of a white dwarf. If we know its effective temperature, we know its cooling age, which is the time that has passed since it started its life as a white dwarf. So this way, if we know the effective temperature, we immediately know the age of the white dwarf, and we can use them to measure time.
Can I ask a question?
Yeah.
Is there a continuum between the A and DB type, in the sense that in some stars you see more hydrogen in the envelope, in some less?
Yeah, it's something that is still there is no consensus about it. The more you get more spectra of white dwarf and more sensitive spectra of them, you start to see these transitional types where you have either DA white dwarf with traces of helium or DB white dwarf with traces of hydrogen. But there still seems to be like the vast majority of the white dwarfs have mostly hydrogen-dominated atmospheres. So the helium ones are around 16% or so, something like that. But there are some transitioning type in between. Okay?
Yep, thank you.
Okay, so I told you that if we have heavier elements in the atmosphere, they quickly sink below that. But how quickly is quickly? So you can see here in this plot that it depends on the white dwarf atmospheric chemical composition and on its cooling age. And we already said that the cooling age of the white dwarf corresponds to its effective temperature. So you can see that here, this is the atmospheric sinking time scale in years as a function of the white dwarf age or its effective temperature. So younger white dwarf have higher effective temperature, and these are hotter and these are cooler white dwarfs. So you can see that helium-dominated non-DA white dwarf, in them it takes more time for the heavier elements, in this case, various types of metals, to sink below the atmosphere, so we don't see them if we take a spectrum of the white dwarf. But there is a region here of hydrogen-dominated DA white dwarf that are younger than 300 megayears, which means that they are warm, relatively warm white dwarf, where the sinking time scale is in the order of days. It means that if we have a small amount of metal that we put on white dwarf, on hydrogen-dominated white dwarf that are younger than 300 megayears, after a few days, if we look back, we don't expect to see any more metals. We expect to see only hydrogen. And if we do see metals in this range, in this regime of white dwarf, it means that something has to feed this white dwarf. So some people took a sample of white dwarf in this range and looked for a metal absorption line in the UV spectrum, where you see where most of the metal absorption lines are. And what they saw, that although they chose only white dwarf from this regime, where we expect to see no metals at all, between 27 to 50% of them do have traces of metals in their atmosphere. And the only thing, the most probable explanation for this phenomena is that these white dwarfs are being constantly fed by metals. So where do these metals come from? It turns out that white dwarf feast on planetary remnants. The white dwarf used to have a planetary system. When it evolved from a main sequence star to a white dwarf, the old planetary system got disrupted, and some of the material got thrown onto the white dwarf, and the white dwarf is slowly, or not slowly, accreting it over time, and it basically eats it. And this gives us a chance to directly measure the bulk chemical composition of exoplanetary material. And this is, I think, the only way we have to do so. So here you can, yeah?
If a chunk of debris falls onto the white dwarf, do you see the metallicity go back to zero after a few days?
If it's a single event, but yeah. I mean, this is the metallicity that you measure from an optical spectrum. The metals are, of course, there, but below the atmosphere. So the fact that we do see this metal absorption line in white dwarf atmosphere means that something has to feed it constantly.
Is the rate of change, when you observe change, does the rate of change, a few days or whatever, agree with the theoretical predictions?
This is a theoretical prediction. The plot I showed you before of the atmospheric sinking timescale is theoretical.
I'm asking an observational question. Did anyone ever observe the metallicity changing on the timescale of a few days?
No, as far as I know, people have tried to see differences in the accretion rates that you get from the equivalent width line of the lines of the metals that you see in the atmosphere, and nobody has found a change yet. So we expect the metals to sink below very quickly. This is from theoretical.
That means that the rate of accreting the rate of debris deposition onto the white dwarf has to be constant. And why would it be constant? I would expect it to
be within our sensitivity, it appears to be constant in, I think, all of the systems that has been observed until today. This is from an observational point of view. I don't think it has to be constant. Obviously, if you have a finite size planetary mass and you accrete it, eventually it will completely evaporate, completely accreting onto the white dwarf. And So theoretically, you should see some difference, but I don't think that anyone has seen any yet.
So if I
Well,
understand correctly,
maybe there's a reason that you don't that it's constant. I mean, maybe the metal-rich debris gets vaporized, but well before it falls onto the white dwarf. And
oh yeah, for sure, it gets sublimated probably. I'm going to talk about it soon.
oh, okay.
Okay. Okay. So if you go back to this plot, it's just a compilation, a relatively outdated compilation from 2014 of 10 white dwarfs, and here you see the colors are of different elements. So basically, you see the chemical composition of each white dwarf. You have bulk Earth to the right for comparison. And you can see that basically we see things that resemble things that we know from our own solar system. We have mostly iron, we have oxygen, silicon, magnesium. So basically, white dwarf gives us the most direct way of measuring the bulk composition of exoplanetary material. Okay, so if we take everything that I've said so far, another thing you need to know is that if you look closely and with very sensitive measurements on white dwarf, you see that more than 50% of them have low level variation with periods ranging from hours to days. And by low level, I mean about 10 to the minus 4 to 10 to the minus 3. And it's something you can't measure from the ground. So, and also from space, it's not that easy. So basically only the white dwarf from the original Kepler mission were observed with this precision. And unfortunately, we're talking about a very small sample of a few dozens white dwarf because the original Kepler field didn't have more than that. And when people, actually Dan Moos et al. Looked at this light curve of the white dwarf from the Kepler field, they saw that about half of them show this low-level periodic variability. So I told you that about 50% of the white dwarf accrete metal from debris, and that about 50% of the white dwarf have show optical periodic variability. So maybe there is a causal connection between these two things. And we wanted to check that. Maybe if the white dwarf accretes metal and it accretes it inhomogeneously across its surface because maybe of a magnetic field, and when we combine it with white dwarf rotation, we might get this optical variability. For example, if we have a fluorescence, we have absorption of the metals in the UV range of the spectrum and then emission in the optical range. This combined with the white dwarf rotation might give us this periodic variability that we see. So we tried to check that, and in order to do so, we took some white dwarf from the Kepler field, some that do have these variabilities and some that do not have this variability. And we got some time on the Hubble Space Telescope in order to take UV spectra of this white dwarf and look for the presence of photospheric metals in their atmosphere. And here you can see an example of how does a UV spectrum of a white dwarf looks like. And you have here this very broad line and alpha line. And the narrow line that you see here, in this case of silicon, are like the metal absorption line, in this case photospheric. The problem is that because of our small sample, we couldn't get a significant match. We were expecting to see metal absorption lines, meaning planetary debris accretion, in the white dwarf that do show periodic variability, and to not see any photospheric metals in the ones that don't have periodic variability, but we couldn't get anything statistically significant. So now what? It might not be the end of that. We still need to explain what causes this variability that we see, and we don't really know yet. It looks like actually most of the white dwarf, even more than 50%, might have these photospheric metals. In this plot, you can see the silicon abundance as a function of the carbon abundance, the measured abundances for a sample of white dwarf. In red, these are the 7 white dwarfs that we measured. The black and gray ones are one from Koester et al. And the triangles are where we have only the upper limits and not actual detections. And you can see that the ones with upper limits measurements are of the same order of magnitude as those with the actual detections. So it might hint us that if we get more sensitive measurements of this white dwarf, we might actually will be able to measure photospheric metals. And another thing is...
Can I ask another question?
Yeah.
I've heard, I once heard that white dwarfs show some circular polarization at some small level.
Yeah, there are not
in the spectra.
There are not many white dwarfs that have spectral polarimetry data, as far as I know, but some of them do show show circular polarization. Some have their magnetic field strength measured, and some do have very strong magnetic fields, but it's very hard to measure the magnetic fields in white dwarf because
I know, but I'm just wondering if the circular polarization also shows periodicity.
I don't think it has been I'm not aware of any such measurement, but I haven't looked into that. So I don't think it has been measured. Sorry?
It would be a good thing to look for.
Yes, yes, there are many interesting things you can do with these white dwarfs. So anyway, we need a larger sample, and we are hoping to get one in the future. The problem is that in order for us to know if there is or isn't an optical variability, we need to have something very precise as the original Kepler mission. Okay, so let's move further about. So until now, we talked about things that are on the white dwarf itself. If we go up a little bit farther away from the white dwarf, there are more evidence of debris. There are about 40 white dwarfs or so that have external infrared emission coming from dust disks. In this plot here, you can see an example of that. You have the spectral energy distribution, the FCD, these are the dots of the white dwarf. And you can see that if you try to fit it with a black body that corresponds to the white dwarf's effective temperature, there is an excess in the infrared, in the near infrared. There is an excess of flux that can be explained if we have a warm, relatively cool dust disk that's coming from debris around the white dwarf. And there are about 10 white dwarfs known that also show metal emission lines coming from circumstellar gas. So this time is not photospheric lines from the photosphere of the white dwarf, but we're talking about gas, some sort of a gas disk or some sort that is surrounding the white dwarf from the outside. And we see emission lines from this white dwarf. Here you can see a nice work by Chris Manser et al. Showing a Doppler tomography map of one of these white dwarfs. They were following up, taking spectra of this white dwarf for years, and they were able to actually map the structure of the disk. However, until now, I mentioned a few things. I mentioned infrared excess emission from debris disk. I mentioned this circumstellar gas. I mentioned the photospheric metal pollution. These all seem to be connected, but we need to have something to connect it to. So, and one white dwarf has all of them. WD 1145 plus 017. It is a white dwarf. It has metal pollution. We see it's one of, I think, the white dwarf with the most heavily polluted white dwarf that is known to date. It has circumstellar gas, that is evident by a metal absorption line. I will show you them later. And it has infrared X emission coming from a dust disk, and it has also transits. It shows transits in its light curve coming from dust clouds. So it was a Nature paper by Vanderburg et al. From 2015, and this white dwarf seems to connect all the dots together. This is a plot from the discovery paper. Here you can see the periodogram of the K2 light curve. K2 was the continuation mission of the original Kepler spacecraft after it lost two of its wheels. And if you look at this periodogram, you see that there are 6 significant peaks showing periods of 4.5 to 5 hours. And basically we have multiple transiting material in these periods. And when they looked at the transits from the ground-based follow-up, what they saw is that the transit shape, here you have the relative brightness as a function of time, you can see that the transits are much longer than expected for a solid body, and they also show asymmetry, and they are rapidly evolving. All of this led them to the conclusion that what we are in fact seeing in this system is a disintegrating asteroid. Basically, we have an asteroid that is just at the edge of the tidal radius of the white dwarf. It's getting disrupted. Occasionally, its pieces are emitting dust clouds, and they are blocking the light from the white dwarf, and this is the transits that we see. Eventually, these dust clouds form a dust disk, and later on, this dust gets sublimated and accreted onto the white dwarf to form this, first to form the circumstellar gas, and then the photospheric metals that we see. So if the transits are caused by dust grains, maybe we can learn something about the properties of those grains by measuring, looking at the white dwarf at different wavelengths. We know that the extinction depends on the wavelength to grain size ratio and on the grain composition. So the idea was to take multi-band fast photometry to look at the white dwarf in different filters simultaneously and to look for changes in the color of the white dwarf. So we got 6 nights with a really cool instrument called UltraCam on the New Technology Telescope in La Silla, in Iso La Silla in Chile. Unfortunately, the weather was not very cooperative, and we were able to observe only on our first and last night, but nevertheless, we got really nice light curves. So these are the light curves we got in this observation from the first night on top and the last night on the bottom. This is the G-band light curve, and you immediately can see a few things. First of all, that UltraCam is a really cool camera, because these are really nice light curves for those of you who have seen some. And you can see that the light curves don't look anything similar between the first and the last night. I can tell you that the features that are highlighted in red are features of the same object. So every night we covered a little more than one orbital period of 4.5 hours. So this is the first transit of the first feature and the second transit of the same feature. Later on, you see it starting to change. And after 5 nights, it already looked completely different, much longer and shallower. And the one highlighted in blue are again of the same transit feature. Again, you see this very rapid evolution of the feature. And the one highlighted now in yellow is new features that appeared out of nowhere, somewhere in between these 2 nights. So this is a really rapidly evolving system. but we were interested in measuring a color difference. So as I said, we used ultracam to look at this white dwarf at 3 different bands simultaneously. So here you can see, for example, the light curve from the second night. And we have here 3 filters, U, G, and I. And you can see that the transit depth in each of the filter is not the same. We got transits that are deeper in the redder band, in the I band, compared to the U band. And this means that during transit, we have more blue flags than red flags than we have out of transit. So we, in fact, were getting bluing instead of the reddening we were expecting because of the dusty environments. But then we had a problem. We had to explain how can we get excess blue flags during transit while we were expecting reddening. Remember that I told you that this white dwarf has circumstellar gas. And here you can see some of its absorption feature. This is from the Shu et al. Paper. For example, if you look at this iron 2 line, the narrow core that you see is coming from the photosphere of the white dwarf. This is the metal pollution in the white dwarf atmosphere. And these very wide and flat shoulders are coming with higher velocities are coming from the circumstellar gas. So another thing is that if you look at the U band and the R band, for example, you can see that, and this is the spectrum of this white dwarf, you can see that there are much more metal absorption lines in the U band than there are in the R band. In the R band, the lines that are marked with blue ticks are helium photospheric lines. This is a helium-dominated white dwarf. So these are not metals, and all these are metal lines from the photosphere and the circumstellar material. So you can see that the U band is much more crowded with lines. And another thing is that if you compare the absorption line, the circumstellar absorption line, in and out of transit, you see that it has different depth. So here you can see in different times, different dates, I think the iron 2 absorption line, in gray, it's out of transit, in pink, it's during transit, and you can see that there is sometimes a significant transit depth between in and out of transit spectra. So if we combine all of these together, we get the following picture. We have the white dwarf that is relatively blue, and out of transit, we see only the white dwarf. And we also have the circumstellar gas that is absorbing more light in the U band, in the bluer range of the spectrum, than it is blocking in the redder part of the spectrum. So the circumstellar gas actually makes the white dwarf look redder than it is. And this is what we see out of transit. And then during transit, we have this transiting debris that is relatively gray. It doesn't really affect the color of the white dwarf, but it's blocking more of the circumstellar gas than it blocks the white dwarf surface itself. So it's actually, during transit, it makes the white dwarf look bluer than it is. And this is the source of the bluing that we saw. So from the fact that we observed this bluing feature, we can learn that the gas and the dust clouds must share at least partially the same line of sight with us, and that the gas, the circumstellar gas, covers the white dwarf only partially. Otherwise, we wouldn't see any color difference. And this conclusion of us was later confirmed by Shu et al., taking simultaneous photometric and spectroscopic data both in the UV with Hubble and in the optical range and in the infrared. And this is basically the explanation for the bluing that we see. Okay, moving on. So this was all about debris, but what about whole planets? Sorry, it went backward. Okay, so can white dwarf host planets in their habitable zone? So the habitable zone, as you know, is the region where water can stay in liquid form around a star. And this is a plot from AGO 2011. You can see here the planet orbital distance, how far the planet is from the white dwarf. And this is the white dwarf age or temperature, as we already said before. And the highlighted region is the white dwarf habitable zone range. We know that white dwarf cool as they age. It means that if they have a habitable zone, it shifts it towards the white dwarf as the white dwarf cools. So the question is, can a planet in a specific location away from the white dwarf can stay inside the habitable zone for long enough time for it to be interesting life-wise? So
how much circumstellar gas is there?
How much what?
Circumstellar gas is there, and at what radius is it, would you say? Do you have any way of estimating?
Yeah, there are some estimation. It's not certain. I think it was something like 100 white dwarf radiuses radii. I can send you a link to a paper because I don't remember the number off the top of my head, but it's pretty close to the white dwarf. Anyway, so inside the highlighted zone, there is plenty of time inside for a white dwarf for a planet to stay inside the white dwarf habitable zone. So planets that reside in this range can stay inside the habitable zone for longer than 3 gigayears. So planets around white dwarf can be interesting, but another reason for that is that the white dwarf is Earth-sized. So if you consider a sun-like star and an Earth, a Jupiter-like planet, we expect to get a transit that is about 1% deep. However, if we have an Earth-sized planet, the transit depth will be about 0.01%, which is very hard to measure. But if you have oh, it keeps getting backward. Okay. But if you have a white dwarf, the white dwarf is the same size of the Earth. Then if you have an Earth-sized planet, you get like a full eclipse, a full transit. So this can be interesting because it's easily detectable. You can use small telescopes to detect that theoretically. And if the white dwarf is close enough to us, so the signal to noise ratio is good enough, because the transit is so deep, we can get transit spectroscopy with a relatively good signal to noise ratio. And this will be a good place to look for biomarkers in the future, like molecular oxygen. Until now, no one has found any planet orbiting in the close to a white dwarf, but we are looking. We got some 3,800 hours of data using the WISE Observatory in Israel and the LCO Global Network of Telescope, looking for planets in the habitable zones of nearby old white dwarf. And currently, I'm going through all this data to look for planets. I'm not very optimistic, but stay tuned. Okay, let's move on to non-planetary stuff. So what about that? Yes.
How close are these close white dwarfs that you mentioned?
You mean how far away from us?
Yes.
About 20 parsec.
Oh.
Very close. Okay, so why should we care about double white dwarfs? There are a few reasons for that, like binary evolution, type 1a supernova progenitors, and gravitational wave sources. In this talks, I am going to focus on type 1a supernova progenitors. So type 1a supernova are important. They are a major source of heavy elements in the universe, and we use them as standard candles to measure distances in the universe, and this is how the dark energy and the accelerated expansion of the universe was discovered. However, nobody really knows exactly what is exploding and how, and this is the so-called Type 1a supernova progenitor problem. Now, we know that in order to get a Type 1a supernova, we need to have a white dwarf with a binary companion, but the nature of the companion is uncertain. The leading scenario until about 15 years ago or so was the single degenerate scenario, in which we have a binary consisting of a white dwarf and the non-degenerate companion. The white dwarf is the degenerate companion, so this is why it's called single degenerate. And the non-degenerate companion can be either a main sequence star, a subgiant, red giant, or a helium star. The white dwarf accretes matter from the companion until it gets to the Chandrasekhar limit, gets unstable, and explodes. In the past decade or so, the double degenerate scenario was becoming more and more popular. And in this scenario, we have two degenerate stars, two white dwarfs in a binary, and they lose energy and angular momentum to gravitational wave, spiraling until they merge and possibly explode as a 1A supernova. Now, if this scenario, if this double degenerate scenario is the main channel to get a Type 1a supernova explosion, if we try to look for its progenitor system, there should be enough close double white dwarf systems to reproduce the Milky Way Type 1a rate. So the idea is to make a census of all the double white dwarf in our neighborhood, and to try to estimate their merger rate and see if it corresponds to the Type 1a supernova rate in our Milky Way, which is about 1 in every 200 years. Another motivation for looking for double white dwarfs is for gravitational wave, because if we have, for example, a double white dwarf binary consisting of two white dwarfs of 0.7 solar masses at a distance of 100 parsecs per mass and a separation of 0.3 solar radius, if we look at the characteristic strain that we expect to get for its gravitational wave signal, it puts us here above the future LISA mission sensitivity threshold. So here you can see the characteristic strain as a function of frequency, and the sensitivity plots of the gravitational wave detectors. This is LIGO, so you can see that the frequency is much lower than that LIGO is sensitive to, but LISA, the future space-based mission, should be able and will be able to see this white dwarf, and it can use it as a verification source. When they turn on LISA, they should see this system if it exists. And white dwarfs that will be farther away from us, double white dwarfs that are farther away from us, will consist the main foreground source of the LISA sensitivity. Okay, so I hope that I convinced you that it's interesting to look for double white dwarf. Now, if you want to look for double white dwarf, one way to do so will be to look for eclipsing double white dwarf in photometric survey. Here you can see an example for such an eclipsing system that we found in K2 data. This system was the sixth known eclipsing double white dwarf when we found it. And the problem is that it's a very inefficient way. You need to spend a lot of time and a lot of telescope time in order to find systems like that. So a more efficient way will be to look for radial velocities variation in white dwarf spectra. Here you can see an example. You have the H-alpha absorption core of a white dwarf taken in 2 different times. And you can see that there is about a 130 kilometers per second difference in the radial velocity of this white dwarf. So the idea is to take a large spectroscopic sample of white dwarfs taken in multiple epochs, and measure the radial velocity differences for each system. And then we get what we call the delta RV max distribution, where delta RV max is the maximum observed RV difference per system. And this is something that Dan Maoz et al. Have done already in 2012 with SDSS data, and they got this distribution that you can see here. So this is a histogram of the delta RV max distribution of white dwarfs from the SDSS sample. And what you see is that this distribution has a very wide core of up to 250 kilometers per second. And systems that are here in the core of the distribution could be either binaries or single white dwarf with just large measurement errors, and we can't tell which one. But systems that are in the tail of the distributions are likely, very likely real double white dwarf. So the idea is to take this observed distribution of delta RV max and compare it to a simulated distribution of a double white dwarf. And this way, maybe we can say something about the actual population. So if we want to simulate the local double white dwarf population, first we need to draw the primary mass. And we do it based on the observed mass distribution of white dwarf. Then we need to decide whether it's in a binary or not. And we do it based on a parameter we called FBin, which is the fraction of all white dwarf in binaries within a specific separation to which our data are sensitive. If it is a binary, then we need to assign it with a secondary mass, which we do based on a power law with an index beta. And as it turns out, our data are not sensitive to this beta. So basically one can take it as equals 1 or 0. And then we need to assign it with a separation, which again, we do based on a power law with an index alpha, which is the separation distribution of double white dwarf at birth. It means that when the white dwarf, the double white dwarf emerged from the last common envelope phase, and we are left with only 2 white dwarfs, what A0 will be its separation. Afterwards, we know exactly how it evolves. It's just spiral in due to gravitational waves. And after 10 gigayears of evolution, the orbit will shrink, and we know exactly how. And finally, we need to assign it with an inclination based on a sin I distribution, and we get this theoretical radial velocity curve for this specific simulated system. We go on and we sample it in a sequence that is drawn randomly from the actual observed sample sequence of observation. We assign it, we noise it with some measurement noise, again, that is equivalent to that of our observation. And finally, we get the delta RV max measurement for this specific system. We repeat it for many, many simulated systems. And then we get these colored lines. So you have here again, you can see in black, the observed distribution of delta RV max of the SDSS, and the color lines are the simulated distribution you get for different parameters. And it turns out that the shape of this distribution is mainly governed by FBin, which is the fraction of all white dwarfing binaries within a specific separation, and alpha, which is the index of the power law of the separation distribution of double white dwarf at birth. If we repeat it for many combinations of FBin and alpha, we get this 1 and 2 sigma contours that you can see here. And the colored solid lines are of constant merger rate. And when Carlos Badenas and Dan Maoz checked it for the SDSS sample back in 2012, what they found is that the double white dwarf merger rate is very similar to the observed type 1a rate in the Milky Way. But the problem is that because of the low resolution of the SDSS spectra, this measurement was uncertain. It could be up to 50 times higher or 10 times lower. So we needed a better sample. Luckily, such a sample exists. It's called the SPY sample. It's the ESO-VLT Supernova 1A Progenitor Survey. It's a large program that was carried out almost 20 years ago on the Very Large Telescope in Chile using the UV spectrograph by Napivotsky et al. And they got high resolution, high signal to noise, multi-epoch spectra, meaning that for each white dwarf, they got a few spectra in different times for about 800 white dwarfs. And here you can see an example for a spectrum of a white dwarf from the SPY sample. So again, we have this black body continuum and absorption Barnum lines. But this time, if we look, for example, on H alpha more closely, because of the high resolution, we can see its narrow NLTE core, and we can actually use this core, line core, instead of these wide wings in order to get a precision of about 1 to 2 kilometers per second. This is compared to the 80 kilometers per second that they were able to get with the SDSS spectra. And this is again the same example. So we repeated the same experiment that Vadenas and Moz have done for the SDSS sample with the SPY sample, and we got this. This is again the delta RV max distribution, this time of the SPY sample. It's one order of magnitude smaller in size compared to the SDSS sample. So in the SDSS, they had 4,000 white dwarfs. Here we have 400 white dwarfs, but we are also can measure the radial velocity to much better. So we were sensitive to separations up to 4 AU compared to 0.05 AU of the SDSS. So on the right, you have the SDSS distribution. On the left, you have the SPY distribution. So you can see that again, we have this core of the distribution that is the result mainly of the measurement error. But this time it goes only up to about 10 kilometers per second compared to the 250 kilometers per second of the SDSS sample. And all the systems in the tail here are double white dwarf candidates. And we have much more of them. And when we combine the results from both surveys, here we have again alpha, which is the index of the power law of the separation distribution of the white dwarf at birth, and F-bin, which is the binary fraction of white dwarfs within 4 AU. You have the 1 and 2 sigma contours in blue for the SDSS sample, in green for the SPY sample, and red is when we combine them both. And the solid lines here are of constant merger rate, and you can see that the white dwarf merger rate is actually much higher than the type 1a rate in the galaxy. Okay, so if we look at it closer, this is the combined contour. You can see that what we learn is that about 10% of the white dwarf that look single are actually double white dwarf separations of up to 4 AU. And that the white dwarf merger rate is about 6 times higher than the specific type 1a rate in the Milky Way. So it looks like there are enough double white dwarf in order to account for the type 1a rate in the galaxy. What does it mean? If we take the white dwarf merger rate that we got and we multiply it by the galaxy lifetime, we get that about 10% of the white dwarfs have already merged. And if we consider that the type 1a rate is about 6 times higher than the merger rate, 6 times lower than the merger rate, what we get is that about 15% of the double white dwarf merger must lead to a type 1a explosion if this is the main channel to get a type 1a explosion. And that about 10% of the white dwarf we see today should be merger products that didn't end up as 1a explosion. Another thing to consider is that in a normal type 1a supernova explosion, we need to produce half a solar mass of nickel-56. But what simulations show us is that you can only achieve this if you have a white dwarf with a mass of at least 0.9 solar masses. Only white dwarf of this mass have the minimal required core density in order to produce half a solar mass of nickel-56. So are double white dwarfs, doesn't tell us anything yet about the mass distributions of this white dwarf, if their masses are enough to have these type 1a explosions. So what's next? We got 97 hours with UVIS on the Very Large Telescope, the same instrument that was used for the SPY sample, in order to follow up all those double white dwarf candidates that were in the tail of the delta RV max distribution. And the idea is to eventually get to orbitally solve these systems. Here you can see one of the systems that were solved long ago, back in 2005. In the original SPY sample, we had only 2 points, or 2 to 3 points for each system. And you can see that in order to get a full orbital solution, you need much more than that. So 42 hours of these were already observed last semester, and 54 hours that are left were supposed to be observed this semester, but due to the coronavirus shutdown, it has been postponed, and we hopefully, I hope we are going to get the time again next year to finish the sample. And also SDSS-5, that is planned to start this year and carried out for about 5 years, is going to get multi-epoch spectra for about 100,000 Gaia white dwarfs, and we can do much more with that. And I'll leave you with the conclusions. Thank you. Any more questions?
4AU is the limit for merger with gravitational waves in a Hubble time?
No, in a Hubble time is much closer than that. We are not interested only in a system that will merge within a Hubble time. It's just because the radial velocity precision that we have for the SPY sample is about 1 kilometer per second. This implies that we are sensitive to systems that are up to 4AU apart. This is just based on the radial velocity precision, because other systems that are farther away than that have much smaller radial velocities.
But then is there a regime of white dwarf binary systems which you can detect and see that they're binaries, but know that they will never actually finish merger, and so should be taken out of the calculation of the supernova rate?
This was the approach in the original SPY program. They were looking for systems that will merge within a Hubble time, but actually also systems that will not merge within a Hubble time can tell us something about the population as a whole. And the merger rate, to measure the merger rate, you just need to assume, we assume this power law of the separation distribution at birth. And from this and the binary fraction, you can actually get the merger rate. Now, there is some observational evidence, and why is the power law a valid assumption? But the reason we are getting this follow-up is mainly to see that the mass distribution of the primary and secondary white dwarf is, we actually don't know anything about the mass distribution of secondary white dwarf in white dwarf binaries. And we also don't really know what is the separation distribution of double white dwarf. This is because until now, the double white dwarf that had been found either by chance or in a biased survey, or they were targeted as extremely low mass white dwarf that can't form within a Hubble time in single stars. So everything that we know about double white dwarf from observations until now is heavily biased and based on very small numbers. This is why we hope that our sample is less biased than the previous ones. And when we finish following it up and solving all the systems, we might be able to say something more clever about the actual distributions of the separations and the masses of double white dwarfs in binaries. And then we can say whether these systems that have larger separation can actually also teach us something about the closer ones. If it's just a Paolo, we can extrapolate it, basically. So this is our hope.
And a second question regarding age. You said that
Yeah.
you can tell the age of a white dwarf by the color, or mass and color temperatures combined.
By the temperature, yes.
So do you take that into account, or is it possible to take into account and to have if you have a survey of these white dwarfs, to classify them by temperature and accordingly age, and then see how that affects the statistics?
You mean the statistics of the double white dwarf sample?
Yeah.
Yes, basically. Okay, first of all, white dwarf candidates are selected based on color cuts, and later on, yes, you can see most of the white dwarfs in our sample are biased because the cooler white dwarf, that are the older ones, are too faint to get a high resolution spectra of. So we will need to take these biases into account, that we mostly see a younger generation of white dwarf. But yes, based on the color or the temperature, you can check also which age biases you have in your sample.
Thanks.
Any other questions?
Sorry, I have a question.
Yeah.
If the merger rate is many times higher than the supernova type 1A rate, then
Yeah.
maybe it means that mergers turn into something other than that. I mean, what else?
Yeah.
What else could they be?
So this is what I said, that what we assume is that 10% of the white dwarfs that we do see today should be double white dwarf merger product that didn't explode. Because if only 15% of the mergers turns into 1As, then the rest should turn into something else. And
well, I mean, if 50 that if 10% if 15% of mergers turn into supernova type 1A,
yeah,
then that leaves another 85% that
right,
into something else.
right, 85% of the 10% double white dwarf.
Yes,
right? It's
yes,
not, yes. So we think that most of them turn eventually, after a short period of evolution, into more massive white dwarf. And there is a debate. Actually, I do have a slide about that. If you look at the white dwarf mass distribution, and this is the mass distribution of white dwarf, of hydrogen-dominated white dwarf from the SDSS, you can see that it has a peak around 0.6 solar masses, and then there is basically not a lot very massive white dwarf. However, it looks like if you take into account also higher magnitudes, meaning fainter white dwarf, you suddenly start to get this peak in the high mass distribution. The difference between the gray and the black is that the gray goes to a bolometric magnitude of 12, while the black ones go to bolometric magnitude of 13. So turns out that massive white dwarfs are intrinsically fainter because they are smaller than less massive white dwarf. And this is why they intrinsically fainter, and they also cool faster after they undergo crystallization earlier on, and then they cool much faster than less massive white dwarf. So it's very hard. So if you have a magnitude limited sample, you are actually biased against having massive white dwarf in your sample. So there is a debate now whether this peak here of the high mass white dwarf is real or not, because it's also very hard to measure their mass from the spectrum because of a lot of also the signal to noise ratio is lower, and massive white dwarfs tend to be more magnetic, and then you can have magnetic splitting in the lines, and it can affect your mass measurement from the spectrum if you don't take it into account. So currently there is a debate whether there is really a high mass bump or not. Apparently there are more massive white dwarfs than we currently know about, and with the Gaia mission it's going to be much easier to look for them and try to find them. We expect naively, based on our numbers, that we should have like a 10% bump in the high mass end of the distribution. But this is something that is currently under debate.
If you don't know the mass distribution, though, how did you figure out that the 15? Oh, that was empirical.
Yeah.
Actually, it may be that, I mean, from the looks of these curves, it may be that you don't get enough supernova from this because most of the mergers would have a combined mass less than the Chandrasekhar.
Right. Right, and this is the main criticism against the double degenerate scenario. And this is another reason why we want to try to characterize the white dwarf mass distribution in binaries with our follow-up that we are doing now. So, because if you have a double white dwarf, the white dwarf that you see, the primary one, is usually the less massive one because it's larger, so it dominates the spectrum. So you could hide a massive white dwarf in a binary where you only see the less massive companion, and probably the secondary the secondary white dwarf mass distribution should be different than the single white dwarf mass distribution. I would assume that the secondary white dwarf mass will be higher than the field white dwarf mass.
I have another question. Can you make a prediction? Can you make a prediction of what mergers would give tidal disruption?
No, I'm sorry, I can't give you any prediction about that.
Because that would be very observable.
Yeah, I'm not sure. I think there are some people trying to do some MESA simulation of how measures of white dwarf should look like. I'm not sure about which transient is expected to be seen during the merger if you don't get eventually a 1A explosion. I don't know. Okay.
Okay.
I enjoyed the talk very much. Thank you.
Thank you.
Thank you. Let's thank Nama again. I'm going to turn off the recording and soon after that retire. But if you guys want to stay here and keep discussing